Hi students, we ran out of time today before I had a chance to go over some key ideas for the upcoming homework assignment. So let's address those now. The first one of those problems I wanted to talk about is problem 612, where they're asking you to determine what is the velocity of water required if we know a flow rate, we know that it's water and it's at a certain temperature, and then also that a force of 200 pounds is required to resist that momentum that is transferred as the fluid jet changes direction. All right, so this is obviously a momentum problem where we've got some force that's arising out of a change of momentum, where momentum is the mass flow rate multiplied by some velocity. So the control surfaces that we're going to have to draw will go around this intersection of the jet and the plate. And so, you look in the x direction, there is a flow in the x direction, but there isn't a flow out in the y direction. Excuse me, in the x direction, because it's changing to the y. So if you look at the equation here, there's no mass flow rate out in x, but there is mass flow rate in the x direction. All right, so then the two things that you have to address are the mass flow rate and the velocity. So first, when it comes to the mass flow rate, that's relatively easy because they've told you the volumetric flow rate, Q, and remember that mass flow rate is Q times the density of the fluid. And for 70-degree Fahrenheit water, we can go to a fluid properties table like in the back of the book in the appendix and find out that at that temperature, water has a density of 1.94 slugs per cubic foot. All right, so if you multiply the slugs per cubic foot density by this volumetric flow rate of 2 cubic feet per second, then you're going to find out how many slugs per second, and that's the mass flow rate, m dot, are flowing in, and that's what we're going to have to use for the mass flow rate in. Now, the force that's applied, this is the force required to hold the system steady, and so that goes directly in to the sum of the forces in the x direction. You'll notice that they're applying the force to the left, and so be cognizant of that. And remember, our sign convention is that forces to the left are negative, forces to the right are positive. So that's going to work out just fine because in the x direction, remember, there's no flow rate out, but there is a flow rate in, and so that minus sign is going to be consistent with the leftward direction of that force. So the mass flow rate you get from the volumetric and the density, and the only thing that's left is finding the velocity in the x direction. So that's the only unknown. Now, just to refresh your memory, a slug multiplied by 1 foot per second squared is a pound force. So if you want to double check the units in this to make sure that when you multiply in your mass flow rate by a velocity that you get pounds, I think you'll find that it does work, and you can prove that to yourself with this units conversion. So that's the main ideas I wanted to share with you for problem 12. Now for problem 29, we have a similar problem. In this case, a fluid jet is intercepting a plate, and part of the fluid continues on, and you'll notice that this smaller jet, the diameter of that is 3.5 centimeters, whereas the bigger fluid jet as it entered was 10 centimeters. And so some of the flow is redirected in the y direction. So you need to find the external force required to hold the plate steady here. And so what we're going to assume is that these jets going vertical, that an equal amount goes up and down, and so that those forces cancel each other out. It's just forces in the x direction that you're going to have to find to hold the plate steady. And the velocity stays the same. So the magnitude of the velocity here, this v is 90 meters per second, and it's still 90 meters per second. That portion which makes it through the opening is still going 90 meters per second. And so the magnitude of the velocity, if we're looking at the out and the in, here's the in stream, here's the out stream. It's not the magnitude of the velocity that changed, and it's also not the direction. But what's going to be different is the mass flow rate. So you're going to have to use the given diameters to find cross-sectional areas. And I think they mentioned in the problem statement that this is water. And so with it being water, then you can look up the fluid density, and you can find the mass flow rate by density times velocity times the cross-sectional area. So this ends up being a relatively straightforward problem once you recognize that the velocity in and velocity out is the same.